Hello and welcome to 6.2. We're going to learn how to create a motion magic controlled intake arm. So right here, I have the base code from the end of chapter 5. You guys might remember that we worked on our shooter subsystem. We had our configurations we had inside of our constants, our PID right here. But today, we're not going to be working on our shooter. Today, we're going to be building on to our intake subsystem that we have right now. So if we want to add an arm to this intake, let's say you have these wheels right here. This is what we were controlling in the past, this intake motor for your spinning wheels. What if you have an intake that you want to stretch and extend outside your bumper to intake a game piece? You'd have to have another motor that could bring this mechanism outward. In this case, we're thinking of an arm. In this case, considering an arm, that means that it might go from, let's say, facing upright and then rotating down by 90 degrees so that it's now touching the floor and can grab whatever game piece you want. First off, we're going to have to change a bit of the naming convention that we have right now. Because we're also going to have an intake arm motor, we want to make sure to rename this intake motor to intake wheel motor so that we understand what we're talking about. In VS Code, if you have a variable, you can right click on it, rename symbol, and then you can type in whatever new name you want. Let's call this intake wheel motor, because this one's the one we have controlling the wheels. If you hit enter, it updates every single one throughout your code. Let's do the same thing with this intake motor ID. Let's rename symbol to intake wheel motor ID. And let's do that again with the configs, since we're going to have some slightly different configs for our arm. We're going to call these wheel configs. We're not going to do this with the current limit because we're going to use the same current limits. So now that we have that set up, let's go on and make our intake arm motor. Just like we did above, you guys know the drill by now. Private Talon FX. We're going to call it intake arm motor. And we're going to say it's a new Talon FX. With device ID, we're going to need to create a new device ID. So let's go to our intake constants, doing a little control hold and then click to go over there. And below where we set up our intake wheel motor and its configs, let's create a few line breaks and create a public static final int intake arm motor ID. Let's see. What's an ID that we haven't used yet? Remember, they all have to have unique IDs. Let's go with ID 10. Let's say we set our intake arm motor to have ID 10. Let's go on after this and create its configs while we're here in constants. We're going to create a public static final Talon effects configuration, just like we did for the wheel configs. We're going to call this arm configs, and it's going to be a new Talon effects configuration so that we're starting off blank. When controlling something with motion magic, we have a few parameters that we're going to need to control. Most importantly are its cruise velocity and acceleration, which, remember, for that trapezoidal move tells you how fast you can speed up to that speed that you're going to hold. Then cruise velocity is the speed that you're going to hold. And yet again, with that acceleration is how fast you're going to slow down from that speed. With our intake arm, that means these speeds are essentially going to be how fast we accelerate our arm moving up, how fast it's going to move at a constant rotational rate, and then how fast we accelerate it back down to stop. Remember that the area under that trapezoid that we'll create by the action is going to equal whatever our motion is. So if we're moving the arm from 0 degrees to 90 degrees, the area under that velocity is going to be 90. Luckily for us, CTRE does all that math for us. So what we're going to do is we're going to add on some configs. You might remember with our shooter that we created a config object here and then added it in with the .width slot 0. Now that you have a little bit of experience with that, we're going to do a slightly more advanced method to save some space. Going on to this line, we can do, yet again, .width. Now, since we're talking about cruise velocity acceleration, motion magic. This sets up our motion magic configs. And instead of passing in an object that we already created over here, we're going to create a new object in this line. A little bit of Java for you. Creating this right here with a new statement inside this line is equivalent to creating an object and then passing it in. For good formatting, I'm going to hit enter and do a few more new lines. Then we have a little bit of indentation so we can tell what applies to what. So inside this motion magic configs, we're going to have .width. Remember now, this .width is applying to the motion magic configs, not the Talon Effects configuration. We're going to do .width, motion magic cruise velocity, and now we need to pass in a cruise velocity. Now the key thing about that value to note is that if you hover over it, you can see its units are in rotations per second. So that means that if you were thinking about in degrees per second, you'd have to multiply by a conversion factor. Let's say we want its cruise velocity when it's doing that trapezoidal move to be 45 degrees per second. We can do units dot degrees to rotations and then pass in 45. Next up, we're going to add its acceleration. Yet again, we can do the same exact thing with units being 45. Realistically, these would be values that you'd tune to your own robot depending on the needs for your season, how fast you need it to be. But that's for you and your team to decide depending on the specific mechanism. Next up, let's add in our PID. So remember, we have these parameters describe our motion magic motion, and then the PID values describe how we get to each point within this motion. So these PID values keep us on target, moving along all those points along the trapezoid, so then we can have accurate motion. So after we have closed this with this parenthesis, remember, this means that this whole chunk applies to our motion magic configs. We can now go down here and do .width slot 0. Remember, slot 0 applies to our PID. You can see here, because this dot is applying after this closed parenthesis, we're actually now talking again about our new Talon Effects configuration. Inside the slot 0 parameter, we're going to add a new slot 0 configs. This is the same exact deal as the motion magic configs. Now, after this, we are talking about slot 0 configs and not a new Talon Effects configuration. So just like we have down here, we're going to need to add in some PID values. Let's give it a .width KP. Remember, these would actually be tuned to your robot, but I'm just going to say KP is 10. .width KI is 0. .width KD is 0.1. And then .width KS, let's give it a static value of, again, 0.1. Remember, these are all random values. You'd need to tune these to your real robot. So now that I've terminated this, this whole chunk applies to our PID. And now I can end with a semicolon, so now we have our ARM configurations. There's one more config that I forgot to add. We're going to add our intake's gear ratio. There's a chance that you have, with a mechanism like an ARM, oftentimes you'll have a gear reduction so that one rotation of your motor is less rotations of your arm so that you can get more torque and the arm can, and that one motor can control a heavier object. The best way to do that is to go through CTRE's methods using .width feedback, and we're going to create a new feedback configs. Now, yet again, we're working inside the parentheses, so we're talking about our feedback configs now. And we're going to do .width sensor to mechanism ratio, because our sensor on our motor, aka how many times our actual motor shaft has rotated, is going to be different than how many times our added mechanism has rotated. Let's just say arbitrarily that this value is 10. We have a gear reduction of 10. Terminating with a semicolon. Let's cut back to the next step. Great. Let's go back to our intake subsystem. Now, after we've done all that, let's fill in the gaps. We can fill in that intake constants dot intake arm motor ID that we created a little earlier. And now we have instantiated our intake arm motor. Here's an important note. When you construct your Talon Effects motor, it zeros the motor. That pretty much sets its coordinate system for the rest of the time that your robot is on. You can re-zero and reset this later, but it's important to note what your mechanism's 0 is, so then you can start your robot with that 0 in a consistent position. I'm going to cut to later me with a little visual of this. This is my Team 1923's robot from 2024. You can see on the back of it that it has an intake that pivots. We called this its zeroed position. Looking at the coordinate axis, we can see that if the intake then pivots downward, it will be seen as at 90 degrees. It's important to keep this 0 in mind because if we started the robot and turned it on and instantiated the motor with it deployed like you can see here, its entire coordinate system would be different, as you can see rotated. If we then told it to still go to 90 degrees, look at its new coordinate system. It would try and run against the bumper and go into the floor. That would not be good. So that's why it's important to make sure that you have a consistent zeroing location and that you keep it in mind. Okay, now that we're back, let's move on to setting up those configurations. Down here, just like we did before, we're going to do intake arm motor.getConfigurator, grabbing its current configuration and applying our intake constants dot arm configuration, that one that we just set up over here. Next up, we're going to do the same thing except with current limits. I'm just going to copy the lines from what we did with our intake wheel motor and change this to be intake arm motor, because remember, we're using the same current limits for both. Now that we have that all set up, let's set up our setter method. So our public void run intake runs the intake at a specific speed, which we had using %out. We're going to create a new method, public void move intake, and this method is specifically for moving this intake arm. We're going to give it a double degrees as its argument because we command it to move a certain amount of degrees. Now to set that up, we're going to need to set our intake arm motor to a specific set control. So what type of control request are we going to need? Well, because we're doing motion magic, a motion magic one. Just like how we set up our shooter's velocity voltage request up top here, for our intake subsystem, up at the top right below where we instantiate our motors, we're going to create a private motion magic, and you'll see, whoa, that's a lot of options. We're going to go with motion magic voltage, which means that it's motion magic that is controlled how we get to the set points via voltage. And we're just going to call it motion magic request. And we're going to instantiate it as a new motion magic voltage with initial position 0. Now let's apply it. Inside this request, we're going to pass in our motion magic request. But remember, this is currently holding that default value of 0. So we're going to add .with position now, commanding it to go to a specific position, degrees. But remember, CTRE's native units are in rotations, so we're going to need to do a unit conversion. You can use units.degrees to rotations, degrees. So now we're taking our degree value passed in, converting it to rotations, updating our motion magic request with that rotation value, and then setting our intake arm motor to move to that position. Next up, let's make a getter. If we're moving our intake, we probably want a getter because then we can know where it thinks it is at a given time. So we're going to create a public double. Remember, we're going to get a double value from it. Get intake position with no argument. This is going to return our intake arm motor dot get would get our percentage. So we're going to do get position to get our position. Remember that this is one of their status signal objects. So if we actually want to get the double value, we can do dot get value as double. And then native units are rotations. So we're going to need to convert this to degrees with units dot rotations to degrees and passing this in right here. So let's make a smart dashboard print out of it. It would be wise in case you want to observe the motion of your intake. So we're going to do smart dashboard.put number with key intake position with get intake position. Great. One thing to note is positive versus negative directions. When you actually test this on your robot, you're going to want to be very careful on the first time you test, so then you can ensure that your arm motor moves as you expect, with the positive direction being what you want it to be. I'd suggest doing this by not actually starting with using a motion magic request, and instead choosing to set up some sort of simple .set command using %out, so then you can control it with a joystick, so you can quickly stop if it is running against a hard stop, or it looks like it's going to hit part of your robot that it shouldn't. You can always change which direction is positive by either negating the value of degrees in the statement, or better practice would be inverting your motor, which you can look back a couple chapters ago to learn how to do if you forgot. Okay, so now we have this method to move our intake. We're almost done. Let's implement this into some of our commands. Looking at our intake commands, if we have our run intake command right here, right now it only moves the wheels. In this command, if we have an intake on an arm, we'd also need to move the arm to the ground before it could actually touch whatever game piece it is. So we've already passed in our intake subsystem, which contains the arm motor, so we don't need to do anything extra with that. But what we can do is add our new method, intake subsystem dot move intake, and we're going to pass in 90 degrees. Let's say we want to fold down to 90 degrees. One thing to remember is that when our command is over, we want to tell it to move back up into our robot. We want it to rotate back to 0 degrees. So let's add in our end, intake subsystem.move intake to 0. That will ensure that it returns. Let's take the same principle and apply it to our intake eject command, doing intake subsystem.move intake to 90 in our execute, running every loop to make sure that it holds that position. And when we end, let's move it back to 0. Now we fully implemented this intake into our code. Remember, we are limited by the capabilities of simulation. There do exist some simulation methods, like I set up here for our shooter, which you didn't see in the original Chapter 5 video, but you can see if you pull our code off of GitHub, where you can actually simulate how this mechanism would move, and it will, with a little bit of extra setup that you can see I added right here for our shooter, will make the motor's sensors act as if there's actually a robot attached. You can see the CTRE docs and also the WPILib docs for more info, but we aren't going to set that up today. For now, this is how to make a motion magic intake. Thanks for watching. See you in the next vid.